Hello dear students, today I will discuss about Taylor's and Maclaurin's theorem with its reminder and also Taylor and Maclaurin expansion of some of the functions. Okay, so this theorem is very important. So here just first of all I will discuss about Taylor's theorem. So here a statement just like Lagrange mean value theorem, the another form of Lagrange mean value theorem having with theta lies between 0 to 1. So here this Taylor theorem is generalization generally. Okay, so just like in the Lagrange theorem, f is continuous and differentiable, continuous, and f dash is dash exists. That is, f is differentiable. This is continuous. This is differentiable, and then there exists point theta lies between 0 to 1, and f a plus h and so on. Just we can write f a plus h equals to f a plus h f dash a plus theta h. This is the Lagrange mean value theorem. Okay, so it's generalization just like we write here. Okay, Taylor theorem. So here the first derivative exists. So here suppose nth derivative exists. Okay, so statement if f n minus 1 x, that is n minus 1th derivative. Okay, n minus 1th derivative exists. Derivative of the function fx is continuous. Okay. In just like Lagrange theorem, f is continuous in a plus h. Here f n minus 1th derivative means n minus 1th derivative of f function fx is continuous, and fn x, that is nth derivative of fx exist in open interval. In open interval a plus h, then what there exists a number at least, then there exists at least one number theta lies between, one number theta lies between 0 to 1, such that f a plus h equals to f a plus, and extend the Lagrange mean value theorem here just up to nth term. So here f a h f dash a plus h square by 2 factorial f double dash a plus h cube upon 3 factorial, or just write and so on, h power 1 upon 1 factorial, h square upon 2 factorial, and so on here up to same h to the power n minus 1, just write here n minus 1 upon n minus 1 factorial up to the n minus 1 term. Okay, so first, second, third up to n minus 1, and this is 1. So n term this, and here just 2, then second derivative, first, then first derivative. So n minus 1, then n minus 1 derivative. And after this n term, just write Rn, where in this, where Rn equals to nth derivative a plus theta h, and here p n minus 1 factorial h to the power n 1 minus theta to the power n minus p. Okay, and this Rn is called remainder. Okay, Rn is called remainder of the Taylor's theorem. This remainder, the value of this remainder given due to Cauchy's, due to Lagrange's, due to Coulombic and Roche, and different type of format of this remainder are given. Here just we use generally Lagrange's form. For that p equals to 10 we take. Okay, so just for proving this theorem we use p. If we take p equals to n, then we get Lagrange's form of remainder. If we take p equals to 1, then Cauchy's form of remainder. If we take p, then this is called Coulombic, Milk and Roche's remainder for the Taylor's theorem. Okay, so just we will use Lagrange's form of remainder. For that, just use p equals to n. Okay, here p is a given number. Okay, where p is a given positive number, and theta lies between 0 to 1. That is very clear that theta lies between 0 to 1. Okay, here this. Okay. So this is statement of Taylor's theorem. Okay. Taylor's theorem. So the value of Taylor's theorem is this, where last term is remainder. Here from first to like this. This is n terms, and after n terms remainder Rn. Okay. So up to the n terms means Rn. Rn means here Rn, then here n minus 1. Fourth term, that is R4, here 3. Third term, that is here 3, here 2. So up to 2 times. If we take n equals to 1, then we get Lagrange's mean value theorem. Just you can see. If here 1, that is just first term is only this, and here f dash a plus theta is. Okay, that is Lagrange's what? F a plus a each for n equals to 1. For n equals to 1 up to the terms. Then what? Fa equals to Fa plus h. N equal to 1 means first derivative exists. Only this first derivative a plus theta h. Thus this is Lagrange's mean value theorem. Lagrange's mean value theorem. And in general, just we write. Then this is remainder R1 for Lagrange's mean value theorem, and remainder due to Lagrange's in Taylor's theorem, just like this. Okay. Here Rn is called, where Rn what? Remainder of Taylor's theorem. Remainders of Taylor's theorem due to Lagrange's remainder is what? Just take p equals to n. If we take p equals to n, then n minus n 0. This will be 1, and p n minus 1 factorial n factorial. So h to the power n by n factorial. Due to Lagrange's remainder, h to the power n. Here n equals to p. Just here p equals to n. This Lagrange's remainder. Due to Lagrange's remainder is equals to, here take p equals to what? N. Then just p equals to n, that n minus n 0, this is 1. P n into n minus 1, n factorial, h to the power n by n factorial, Fn a plus theta h. Okay. So this is Lagrange's remainder. Just we will use this remainder for solving questions. Okay. So this is the statement of Taylor's theorem. Okay. So the statement is very, very important, and also proof is important. Just like algebraic proof of Lagrange's mean value theorem, we can prove it by taking a function, considering a function, and satisfying all that condition of Rolle's theorem by that function, and then we can get this type of relation. Okay. So here just we have to prove this theorem. Very, very important. 3-4 step is required for that. Okay. So just a start. This is a statement and proof. Proof is simple. Just we write terms up to nth time. Okay. Here given that n minus 1, n minus 1 derivative is continuous. Okay. n minus 1th derivative is continuous. So we can write consider a function for continuity of that function, just we can combine it. Okay, so proof. Proof of Taylor's theorem. Okay, so here, since in the statement, since n minus 1 exist, n minus 1 derivative, fn minus 1 means another derivative exist, n minus 1 derivative of the function exist, therefore n minus 1 derivative exists in exist and continuous in a plus this interval. It is given in a statement. Another n minus 1 derivative exists. Another derivative also exists in open interval, but this derivative exists and continuous in closed interval. Therefore, f dash, f double dash, f n minus 2 dash also continuous in a plus h. Okay. Means n minus 1 derivative exists and continuous. So its lower derivatives are there and also function. Therefore, these are also continuous. Okay, in closed interval. So let us define or consider. We can also write consider. Okay, so let us consider a function phi x as, just we consider a function phi x, because all these are exist, so we can write like this: f a plus, we are having interval a plus h, so a plus h minus x, f dash a plus a plus h minus x square upon 2 factorial f double dash a, up to, just write here what we can write, just see, because fx, sorry, this is fx, just we define like this, because all these are continuous, and this is also continuous. So we can combine this function fx, f dash x, f double dash x up to fn minus 1x, up to a plus h minus x. This is given number in interval, so minus x power n minus 1 upon n minus 1 factorial up to this time. All are exist. So here we can use f n minus 1 x plus a plus h minus x power p constant a. Just we consider, because we are having this type of up to this n minus 1 derivative, that is n minus 1 derivative of function. So these are all exist and continuous, and just we can combine this type of combination. This is also continuous, and after this term, okay, just after this term, write this a plus h minus x to the power p a. Here p is a, here p is a given positive number, positive number. Okay, just write this. Clear? Here, suppose this is equation 1. We have to prove Taylor's theorem. For that, just this is given in a statement in this interval. So just we suppose we consider this function up to here, from here to here we can combine, and this last term take like this. Okay, this is our supposition. Okay, such that let us consider function phi x this such that phi a equals to phi a plus h. Just we suppose this type of function, and suppose phi a equals to phi a plus h. This condition is required for finding value a constant here. Okay, this up to this n terms, and this is n plus 1 term. Clear? Now here phi a equals to phi a plus h. This is our supposition. Now just we see that this is constant, a plus h minus x to the power p is this term. So up to the from here to here n terms are related with continuous function n minus 1 derivative. This is polynomial type relation, so also continuous. So this combination is continuous. Also this is continuous because this is constant, this is polynomial type. So this is continuous function, we can say in the interval a plus h. First. Second, this, because we suppose this function with a constant. For determining constant, just we write this. So let us consider function this such that this. Clear? Now for getting phi a plus h from this function, put x equals to a in 1. Then forgetting this. Okay. phi a equals to, just put phi a in place of x, a, all a, that is h. A means a cancel h. In this combination there will be h, and here x, a. So fa plus h f dash a plus h square by 2 factorial f double dash a plus here h to the power n minus 1 upon n minus 1 factorial f n minus 1 derivative of a plus here h to the power p, h to the power p into a. This is phi. Also put x equals to a plus h in 1. In this relation, in place of x, just put a plus. For getting these two value, and by using this relation, we will get some other relation. Okay, here phi a plus h in place of this a plus h. So x a plus h. Okay, here a plus h 0, a plus h 0, 0, 0. All terms are vanishing. So here phi f a plus h plus 0 plus 0 plus 0 plus and so on up to 0. So this is equals to what? F a plus h. So phi a plus h. Just equate this two value. Equate this two value. Okay. Now equating from equation 2, phi a and phi by using above value of phi a and phi a plus h and equation 2, we can get what? See here, this is our supposition. Okay. Now this is the value of phi a plus h. Just use this phi a plus h and this equation. So we can write what? Okay. So using above values of phi a and phi a plus h, with equation 2. Just equation 2 means phi a equal to phi b. Equation 2 means phi a equals to phi b. With equation 2 we get, okay, phi a equals to phi b. That means this equals to this. Just we get what? Just like this, using above values of phi a and phi b means this phi a and phi b, phi a and phi a plus h and equation phi a equals to phi b. And with equation 2 we get, after this line just we write here, okay, what phi a equals to value and phi a plus h both are equal, that is phi a plus h equals to f a plus h. So f a plus h equals to, just like phi a means here f a plus h f dash a plus, just you can see, okay, h square by 2 factorial f double dash a plus up to, which term is there, h to the power n minus 1 upon n minus 1 factorial f n minus 1 what a plus h to the power p into a. So just we get like this way. Here phi a plus h, and phi a equal to phi a plus h. Now, okay, we get this relation just using equation 2 we get this. Now suppose this is equation 3rd. Now for proving Taylor's theorem, here for the function phi, just we get two relation. What? Of Rolle's theorem. The function is continuous in open closed interval a plus h. Just we see that this is continuous, we can say, and phi a equal to phi a plus h. And one other condition is what? Differentiable. Okay, so its derivative should be exist. Okay, after this line, just write differentiate one, we get its derivative. Okay, what? Phi dash x with respect to x, just differentiate f dash, its derivative f dash here, product of two function f dash, first function, second function, derivative of first function minus 1 minus second function, and then derivative of this and this, so plus a plus h minus x into f double dash. Similarly, its derivative, first function into second function, so its derivative is what? 2 of this minus 1, so minus 2 to cancel, a plus h minus x f double dash, and plus its derivative, and it is as it is, so a plus h minus x square upon 2 factorial f triple dash x, clear, and minus, and so on and so on. Just differentiate total function. Then here we see that this cancel, this cancel. Similarly, this minus of this, and from each term you can get two terms. Just one term from first, one term from second, or will be cancelled. So this is cancelled, this cancelled, and up to last what? Its derivative at the last instance. So its derivative is what? P. So P a plus h minus x to the power p minus 1. Okay? And minus 1 into constant. Last term. and before and that this term just its second term. Here we write, okay, its second term. Second term is will be what? Second term is just positive. So as it is, and n minus 1 derivative will be n. At the time of differentiating this, just first time part will be derivative of this into this plus derivative of this into this. So that part is here plus a plus h minus x to the power n minus 1 upon n minus 1 factorial f n x. Okay. So this is its derivative here. And also before this all terms will be cancelled, because for a term just this remains, its first term will cancel from the here. So its first term up to this term will be cancelled. So we get what? Phi dash x equals to this a plus h minus x power n minus 1 upon n minus 1 factorial fn and a derivative x plus p a plus h minus x power p minus 1, here minus sign into a. So just we get this. This constant, this exists because p is a given positive number. So it is exist also, it is exist also. So derivative and a derivative exist in open interval. It is given in a statement in the condition of the Taylor's theorem. So it exists. So this is exist, this exists. That means which will exist, in open interval, because another derivative exists in the given statement. So this is exist, derivative exists. Okay, so derivative exists here. Clear? Now we get that, or we can write like thus. We see that all the three conditions of Taylor's theorem, Rolle's theorem are satisfied by phi x. Okay. Thus we see that all the three conditions of Rolle's theorem Thus we see that all the three conditions of Rolle's theorem are satisfied by the function phi x. All three conditions of Rolle's theorem are satisfied by the function phi x, as phi x is continuous in a plus h phi x is differentiable in a plus h and differentiable, okay, and phi a equals to phi a plus h. Therefore, according to Rolle's theorem, there exists at least one number theta lies between 0 and 1 such that because we know about Rolle's theorem, if three conditions are satisfied by a function in Rolle's theorem, then we can write what? Phi dash c equals to 0. Phi dash c equals to 0. That is, c can be written as in a plus h. So c can be written as a plus theta h. Theta lies between 0 to 1. So we can write in place of c theta. Theta lies between 0 to 1 such that what? Phi dash a plus theta h equals to 0. Clear? Phi dash c equals to 0. That is, phi dash c equals to 0. C lies between a and a plus h. A and a, c can be written as a plus theta h. Okay. So just we get this. Now, from here, just see the derivative of phi x. What was that value? Just use derivative. Phi dash. Just phi dash x equals to x in place of x. Here, just derivative was what? A plus h minus x. So here, a plus h minus x in place of x, a plus theta h. A plus theta h in place of x power n minus 1. Just use the derivative. Just we have got here. Okay. So this upon what? N minus 1. F n. In place of x, a plus theta h minus p, a plus h minus a plus theta h, p minus 1 into a. This. Just put the value a plus theta h for x in the derivative. So this is left side is equals to 0. This is equals to 0. From here we see that value of a, constant a equals to what? A equals to, just transfer to right hand side and that's a equals to, you can write here. We see that a cancel h minus theta h power n minus 1. So we can write after taking common n h to the n minus 1, 1 minus theta to the power n minus 1. here Fn A plus theta h upon this upon n minus 1 also factorial, and right hand side, transferring right hand side, just p and this quantity will go to the denominator. So p here and here a cancel a, same as h to the power p minus 1 and 1 minus theta power p minus 1. So just like this. Okay, so this value will give constant a equals to. So it can be written as, after reducing h to the power p minus 1, h to the power n minus 1. So we can write minus 1 cancel, n minus p. 1 minus theta to the power n minus 1, p minus 1. So 1 minus cancel, n minus p upon here p n minus 1. So here just we can write h to the power n minus p, 1 minus theta to the power n minus p upon this upon n minus p adjust n, and here p n minus 1 factorial fn a plus theta h. Okay, so this is the value of constant. Now put this value of constant in equation third. Okay, using this constant in equation third, we can get Taylor's theorem. Okay, which is h equals to not 0 and 1 minus theta equals to also not 0. So here we can write this is the proof of our Taylor's theorem. Okay, so here we see that if we put the value of constant in equation third, then we can get the Taylor's theorem. Okay, with remainder at the as the last term. Okay, so here put the value of a in third, we get in third means third equation. In this equation just put a equals to, so we get what? F a plus h left hand side equals to fa plus h f dash a plus square by 2 factorial. H to the power 1 by 1 factorial. F double dash a plus and so on. Just this term is here. H n minus 1 upon n minus 1 factorial. F n minus 1 a plus h to the power p into this h to the power n minus p one minus theta n minus p upon this upon p n minus 1 factorial f n dash into fn a plus theta h. Okay, just you can write fn a plus theta H. This nth derivative. Just put this value here. So this is Taylor's theorem. Here, last term is denoted by Rn. This term is denoted by Rn, remainder. Okay. So here we denote, just we can write in, it can be written as Rn. Okay, so we get Taylor's theorem as this. We get f a plus h equals to, just write, I'll write this equation here for a phrase, f a plus h f dash a plus h square by 2 factorial f double dash a plus up to h power n minus 1 upon n minus 1 factorial f1 a plus Rn. Just we can write after this term, this is Rn. Rn equals to what? H power pp cancel h power n and remaining thing are there. Okay. So where Rn equals to h power n 1 minus theta power n minus p upon p n minus 1 factorial fn a plus theta h. H equals to not 0 and 1 minus theta equals to also not 0. Okay, this clear? So this is Rn is called remainder of Taylor's theorem. This is the proof of Taylor's theorem, and also this is Taylor theorem where Rn is called remainder of Taylor's theorem, and remainders are given by different mathematicians like Cauchy, Legendres, and another name is what? Sklomilk and Roches. This is called Sklomilk and Roches remainder. Just we will use always Lagrange remainders. So Lagrange's form of remainder for Taylor's theorem is given by Rn equals to h to the power n upon n factorial Fn a plus theta h. That is taking p equals to n. When we take p equals to n, then the form of remainder is known as Lagrange form of remainder. Lagrange form of remainder. Causes remainder, just take p equals to 1. This is called, in terms of p, Coulombic remainder. Coulombic, what is the name? Coulombic and Roche. And Roche's form is this. Okay. Coulombic and Roche's form of this remainder. Lagrange's form of remainder is this. And when we take p equals to 1 here, then Cauchy's remainder form is just taking p equals to 1. P equals to 1. So here p equals to 1 means h power n upon 1 minus theta power n minus 1 upon n minus 1 factorial Fn a plus theta h. This. Okay. This is 1 minus theta power n minus 1 factorial, like this. Okay. This is Cauchy's remainder. Just we will use always Lagrange's form of remainder for Taylor's theorem. Okay. So this is the generalized Taylor's theorem with remainder form. Whenever we use Taylor's theorem with Lagrange's form of remainder, just you have to write after this term here Rn as this. Expand the function or write the Taylor theorem for with Lagrange's form of remainder up to the 4th term, that is n equals to 4. Up to the 3rd term, that is n equals to 3, Rn. Yeah, 3. Okay, 3rd derivative. Here 3, that means here 2. Here 4, that means here 3. So this is the form of writing of Taylor's theorem up to the specified term. The 2nd term, 3rd term, 4th term, 5th term. Okay, so these are the remainders of Taylor's theorem. Okay, now there is another form of, this is the writing of Taylor's theorem with Lagrange remainder. We can write, just use Lagrange remainder. We have, okay, what? H to the power n upon n factorial Fn a plus theta h. This is Lagrange remainder form. Okay, so this is Taylor theorem. So Taylor's theorem with Lagrange's remainder form is this. Okay. So this is our Taylor's theorem. Now just From this theorem, okay, this is Taylor theorem. Now it's another form. Just we have to see what is the another form. This is first form. Second, Taylor formula. We can say also Taylor formula up to nth term for n equals to n. And you can write also n equals for particular terms here there. So suppose if here if we take what a plus h equals to x, that is in the interval here, just like a plus h is our interval, so here just write x, ax interval, first a and then x, this, then h equals to what, x minus a, so we get very very important form of Taylor's theorem. Here f x, just write a plus x equal to h, x, just here in place of h write x minus 1. So fa plus h means what, x minus a, f dash a plus x minus a square by 2 factorial, f double dash a plus and so on, plus x minus a or n minus 1 upon n minus 1 factorial, f n minus 1 a. Just write in place of h x minus a, and last term will be what, x minus a or n upon n factorial and fn a plus theta h. Clear? So this is second form. Theta lies between 0 to 1. Theta lies between 0 to 1 always. Theta lies between 0 to 1 always. This is second form of Taylor's theorem. Okay? Which is called Taylor theorem or Taylor's formula about the point A. Clear? This is Taylor's formula, or you can say Taylor theorem, because remainder form is also there. So where theta lies between 0 to 1. This which is called Taylor's theorem or Taylor's formula about the point x equal to a. Here x minus a, x minus a, x minus a. That is, whenever the question as just expand the function or write the Taylor formula, Taylor theorem about the point x equals to 2. About the point x equal to 2. That means a equals to 2. about the point. This is about the point x equal to a. X equal to a means what? X minus a. A equals to 2. A equals to 2, then x minus 2 of this power, x minus 2. 3, then 3 power. So just about the point a. Okay. This is the Taylor's theorem or formula about the point x equals to a. Okay. The function can be expanded in the powers of x minus a. Okay, up to this term, this Taylor formula. Now, in a special case of Taylor's theorem, very important here, if we take a equals to 0, if we take a equals to 0 in above Taylor's theorem, we get what? We get Maclaurin's theorem. We get what? Fx. Just first point here. Interval is what? A plus h. Take it x and take it 0. That is what? Meaning is a equals to 0 and h equals to x. H equals to x. In this case, what is the format of this theorem? Very special theorem, that is called Maclaurin's theorem. So here f0. In place of a, just write 0. f0 plus. Here a equal to 0, that is x. f dash 0 plus x square by 2 factorial f double dash 0 plus, and so on, x to the power n minus 1 upon n minus 1 factorial f n minus 1 0. Just write in place of a 0, and last term will be what? X to the power n upon n factorial fn theta x. Theta x, because in this case what? A equals to 0, and if a equals to 0, then h equals to x. So a plus theta x means 0 plus theta x. So this is, which is known as Maclaurin's theorem. Maclaurin's theorem, and its remainder, Lagrange's form remainder, is what? Last value, x to the power n upon n factorial fn theta x. This is R. Lagrange's form remainder of Maclaurin series is this. Okay, so this is Maclaurin. Very important. Maclaurin's theorem, or this is Taylor's theorem. The special form. Taylor's theorem expanding about a point A. Maclaurin about the 0, that is about origin. What about A? About A equal to 0, origin. So Maclaurin theorem is what? Taylor expansion of the function about origin, we can say in other words. So here, this is remainder of Maclaurin's theorem. Lagrange's form remainder is this. Here, This is reminder for Taylor theorems about x equal to a, and this is also Taylor theorem. So these three formula are very important. So remember, these are the formula for solving questions. Okay. So Taylor's theorems and Maclaurin's theorems are stated here like this. Okay. So for writing Taylor's theorem, Maclaurin's theorem, up to a special term, just third term, fourth term, fifth term, then n equals to 3, 4, 2 and so on. So just now we will solve some questions related to this theorem. Okay. So this is very important, so note down it. Okay. And here, just one thing is, for solving questions, we can expand any given function as an infinite series. If suppose, here just what is this? The nth derivative. In the Taylor theorems, it is given that nth derivative exists. If what will be the value of n? How many times? N times. N tending to infinity or not? That is first term, second term, third term, fourth term, and up to the nth term. So how many terms any function can be expanded up to how many terms? If, because at all times it is impossible to find the derivatives of all orders. So how many times just we have to take the terms of the expansion of a function. So here nth derivative, that is, this is remainder form, just we write as a remainder form. So if remainder can tend to 0, if remainder can be tending to 0, then we can say that the theorem can be written up to the infinitive terms, as many as terms, as following this process. Just you can see that here is a one thing. What x is power 1 by 1 factorial, 2 by 2 factorial, 3 by 3 factorial, 4 by 5 factorial, and first derivative, second derivative, third derivative, fourth derivative, up to the any time of derivatives. If remainder tending to 0, as n tending to infinity, that means number of terms tending to infinity. That is, if n tending to infinity, just if we can show that if remainder tending to 0, that is Rn tending to 0. Okay? As n tending to infinity, then you can write it as an infinite series. So here we can say that the Taylor expansion or Maclaurin expansion can be written. Taylor expansion and Maclaurin expansion can be written Taylor expansion and Maclaurin expansion. This is Taylor expansion, this is Maclaurin expansion. This, if function can be expressed as an infinite series, or if all the derivatives, the function having all the derivatives, and also remainder tending to 0 as tending to infinity, then we can write the Maclaurin series and Taylor series as infinite terms. So here we can write like this. Taylor's expansion. Maclaurin is Maclaurin expansion is Taylor expansion of it is possible if all order derivative exist and Rn tending to 0 as n tending to infinity. Taylor's expansion of fx, if all orders derivative exist and Rn tending to 0 as n tending to infinity, then we can write in a similar way n factorial fn a as infinite series. Okay, here also x minus a power n upon n factorial fn a infinite x to the power n upon n factorial fn 0 just this. Here also. Okay. If all order derivatives if all order orders derivative, yeah, derivative of all orders, okay, just we can write as if derivative of all orders, if derivative of all orders exist and remainder tending to 0 as n tending to infinity, then we can write like this. That is same expansion, just take up to the infinity, take up to the any number of terms, because all derivative of all order exists then. Okay, so these are the expansion formula of a function. Okay, so here what possesses derivatives of all orders and remainder tending to 0. So take some questions. The first question as just first question is verification of Taylor theorem. Okay, so verification of Taylor theorem, just like verification of Lagrange mean value theorem, Rollet theorem, just we see, we state, first of all, we see that whether the condition for Taylor's theorem or Maclaurin's theorem are satisfied or not. The Maclaurin's theorem is what? Just particular case, that is a special case of Taylor's theorem. So the condition of Taylor's theorem is also for Maclaurin's theorem. Okay, so here just solve some questions. First question is take here what? Verify Taylor's theorem for the function fx equal to this with Lagrange's form of remainder up to two terms in the interval 0, 1. So here solution of first question. Okay. Given fx equals to 1 minus x to the power 5 by 2. This is the given function. Okay, given function is what? 1 minus x to the 5 by 2. Clear? And intervals. And interval is what? 0, 1. Interval 0, 1. Lagrange's form. We have to verify. Taylor's theorem. Taylor's theorem with Lagrange's form remainder up to two terms. Up to two terms. Okay, that is what? Up to two terms. Just taking two terms. So here we know that Taylor's theorem up to two terms with Lagrange's remainder form as follows. What? F x equals to f a plus x minus a f dash a plus x minus a square by 2 factorial f double dash a plus theta h. Theta lies between 0 to 1. That is, what is this? Just here up to second term. Up to second terms, that means R2. R2. Just you can write up to R2. Okay. Here you can write up to R2 just like this. What? R2. Where R2 equals to x minus a power 2 by 2 factorial f2, that is you can write also double dash a plus theta a plus theta x minus a. Here just see that first value is a, and here a plus h is x. Here a, that means what? Interval length is h. So h is equals to what? X minus a. So a plus theta h, h means x minus a. Clear? Theta h, h means x minus a is there. Okay. So this is the value of remainder. So we can write here interval is 0, 1. So we take what? A equals to 0 and a plus h equals to x equals to 1. Is this? Therefore, we get what? Fx equals to f0 plus h equals to 1, x, this is x equals to 1. So here just we can write f0 plus x equals to 1, a equals to 0. So 1 into f dash 0 plus r2. R2 can be written like this. What? 1 square upon 1 minus 0, 2 factorial, f double dash a equal to 0 theta into 1. Okay. So this implies fx equals to f0 plus f dash 0 plus 1 upon 2 factorial f double dash theta. Now we have to verify Taylor's theorem. That means value theta must lie between 0 and 1. Now fx equals to 1 minus x to the power 5 by 2. So its derivative what? F dash x equals to 5 by 2 1 minus x to the power 3 by 2, and also minus sign with minus sign. And second derivative f double dash x minus minus plus 3 by 2 also 15 by 4 1 minus x to the power 1 by 2. So these are the values because fx is given, fx this, f dash x this, f double dash x this. So just we require f0, f dash 0, f double dash theta. So here from this f0 equals to what? f0 equals to 0. Here f dash 0 equals to f0, no, sorry, this is 1. f0 equals to 1. f0 equals to 1. f dash 0 equals to what? Minus 5 by 2. Minus 5 by 2. Here what? F double dash theta. So f double dash theta is equals to what? 15 by 4. So 15 by 4. 15 by 4. 1 minus theta power half. 1 minus theta power half. So these values just you have to put here and find the value of theta. If theta lies between 0 to 1, then Taylor's theorem is verified. Okay. So now, after this, just this. Put all values in 1. We get all values in 1, that is this. That also f1. Because x equals to 1, no? X equals to 1. X equals to 1. So here x equals to 1. So f1. F1 also find f1. Also f1 equals to, because f1 is required also, na? Here. So f1, what? X equal to 1. So f1 equals to 0 because f1 is also required. X equal to 1. So f1 equals to 0. So just put value in this 1. f1 is 0. See, let's try 0. So 0 equals to, just solve it. f0 equals to what? 1. Now f dash 0 is this. What? Minus 5 by 2. So minus 5 by 2. And f double dash theta equals to this. 1 by 2 factorial. 15 by 4. 1 minus theta to the power 1 by 2. Just solve it. We can get 0 equals to 1 minus 5 by 2. 1 minus 5 by 2 means what? 2 minus 5 minus 3 by 2. And here just plus 15 by 8. 1 minus theta power half. So just we see that 1 minus theta power half equals to what? 3 by 2 into 8 by 15. So this is equals to what? 4 by 5. So just solve it. Okay. Here we can get the value of theta. So implies 1 minus theta is equals to 16 by 25. Squaring on both sides. So theta equals to 1 minus 16 by 25. 25 minus 16. 9 by 25. 9 by 25 equals to, just you can divide it. Okay. 9 by 20, 0.36. 0.36. 9 by 25. 0.36. Okay. Which, this is the value of theta. So theta equals to 0.36, which is which lies between 0 and theta, implies Taylor's theorem is verified for given function. Okay. So this is the verification of Taylor's theorem. Theta lies between 0 to 1. Okay. Now take second question. Here we can second question is, so very simple here. Just like this question, you can verify also Maclaurin theorem up to required number of terms as remainder R2, R3, R4 and so on. Clear? Maclaurin theorem can also be verified by finding the value of theta between this and this. Okay. So here just this type of question may be here also. Just state or write the Taylor formula or Maclaurin formula or Taylor theorem or Maclaurin theorem with Lagrange's form of remainder for the given function, just like this. Okay, so here for the given function sin x, so just state Taylor's theorem or Maclaurin's theorem of Lagrange's remainder form for the function fx equal to sin x. So this take this question. So solution, given function, given fx equals to sin x. This is the given function. Just we have to write Taylor's Maclaurin's theorem. Just we have to write Maclaurin's theorem for the function fx equal to sin x. Okay, with Lagrange's form of remainder. So here, just see, we know that Maclaurin's theorem with Lagrange's form remainder is what? Fx equals to f0 x f dash 0 x square by 2 factorial f double dash 0 up to x n minus 1 upon n minus 1 factorial f n minus 1 0 plus up to the remainder what? Up to the remainder Rn, where Rn equals to x to the power n upon n factorial fn theta x. This is remainder, Lagrange's form remainder. Just we have to state, we have to write Maclaurin's theorem or Maclaurin's formula for the given function sin x. Okay, so just for this, find f0, f dash 0, f double dash 0, f n minus 1 dash 0, and then finally fn another derivative, and just write like this. Here fx equals to sin x. Okay, this just differentiate it first time. Okay, so implies f dash x equals to, first time differentiate what? Cos x can be written as sin, can be written as sin was x plus pi by 2. Sin 90 plus x equals to cos x, and positive in second quadrant. So just we can write this. Second derivative, just again derivative, differentiate it, minus sin x. Its value, no, just this, sin cos x plus pi by 2 into 1 into this. So cos x plus pi by 2. So this can be written as sin x plus pi by 2 plus pi by 2 is equals to what? Sin x plus 2 into pi by 2. Similarly, we can see that nth derivative of x is equals to sin x plus n pi by 2. Because 1 time differentiate, just 1 pi by 2. 2 time differentiate, just 2 pi by 2. 3 time differentiate, 3 pi by 2. N time differentiate, n pi by 2. This is nth derivative. Clear? Now, just we have to write first derivative, second derivative, third derivative, odd order derivative, even order derivatives. So here we see that for the last term, okay. So suppose we can find here if we take here this implies 2n, just take in place of n 2n, x equals to what? Sine x plus 2n pi by 2 equals to what? Sine x plus n pi. This can be written as sin a plus b formula. So sin x cos n pi plus sin n pi cos x. Just we can see that sin n pi is 0 always. Cos n pi minus 1 to the power n sin x. So this is equals to minus 1 to the power n sin x. Just we get this f to n x equals to this, implies f to n derivative of x is equals to this, second order derivative, even derivatives, and just odd derivatives also. F to n minus 1 x, just before term, see here, what can we get? Sin x plus, in place of n, 2n minus 1, see here 2n minus 1 into pi by 2 is equals to what? Sin x plus 2 to divide, just 2n pi n pi minus pi by 2, minus pi by 2, like this. Just by, we can write also like this, minus sin pi by 2 minus x plus n pi. So this is equals to what? Minus sin 90 minus theta cos theta. So cos x plus n pi. It can be solved. Okay, it can be solved. How? Minus just cos x into just we can see here, because last derivative just we have to write, so we can use this for, and before this term just odd order term before the first term. Okay, so what will be the value here? Just cos a cos b, cos x into cos b means in pi minus 1 to the power n minus sin a sin b, sin n pi 0 0. So this is equals to minus 1 to the power n cos x. Okay, this implies f to n minus 1 x equals to this. So because it's for solving it, just we are using 2n time and n minus 1 time. By taking that, you can solve it. Okay. So here, for using this, just we have to state this theorem, no? Right. So just find f0, f dash 0, f double dash 0, f triple dash 0 and so on. So here, now, f0 is equals to what? Fx equal to sin x, sin 0 equals to 0. F dash 0 equals to what? Up to first two terms, just write. F dash 0. What is f dash 0? N. Just see here. F nth derivative at 0 equals to sine n pi by 2. Just you can use it. Because in place of x, just write 0. So n equals to 1. Now, that is what? 1. Sine 91. 1. F double dash 0. Just here n equals to 2. 2 sine pi. What? 0. F triple dash 0. Here 3 sine 3 by 2. Sine 3 pi by 2. What will be the value? Sine 3 by pi by 2. Sine pi plus pi by 2. This is equals to what? Pi plus sine pi plus pi by 2 minus 1. Minus 1. Similarly, 4 dash, just 4 sine 2 pi 0. And so on. You can find all the derivatives. And also, from here, if 2n minus 1 0 equals to cos 0 minus 1 to the power n. Okay, even power minus 1 to the power n sin x. Just nth derivative we also require for remainder. So we can write just use all these values. Okay. Use all these values here. F 0 equals to 0. Thus, using all these values, and also you can find as a last term Rn, what in place of n 10th term, just like this, up to writing in 1. In 1 we get what? Fx equals to f0 0, f dash 0 1 x 0 plus x, second 0 plus 0, third minus x cube by 3 factorial. Okay, and again what? 0 for derivative 0 and so on up to plus x to the power 2n minus 1 up to the term 2n minus 1 upon 2n minus 1 factorial. Okay, 2n minus 1 factorial. So here what will be the value? F 2n minus 1 0, f 2n minus 1 0 plus x to the power 2n plus 1 upon 2n plus 2n factorial and f 2n theta x. So this will be the formula here. So just write finally fx equals to x minus x cube by 3 factorial. Just as a similar, we can get next term, fifth term. Also you can see that fifth term, what will be the value of fifth term and a derivative. So x or 5 by 5 factorial minus and so on up to similar. Here f to n minus 0, f to n minus 0, 0. So cos 0, cos 0 1, cos 0 1. So minus 1 to the power n. So just for writing this series here, minus 1 to the power n minus 1, we can write it also minus 1 to the power n plus 1, also minus 1 to the power n plus 1 or n minus 1, because in both cases this will give same value. But n minus 1, because of that, x to the power 2n minus 1 upon 2n minus 1 factorial f, this is value, this value is completed. Now x to the power 2n upon 2n factorial, now this value comes from here, f2n theta x, here theta x, here theta x. So just write in one time minus 1 to the power n, and here sine, and also this x to the power 2n upon 2n factorial sine theta x, this. Okay, so here theta x, just put here theta x. Okay, and minus 1 to the power n is there also. So just putting this is Maclaurin's formula or Maclaurin's theorem, which is required Maclaurin's theorem for given function. Okay. Clear? So this is the result. So here just last time here 2n minus 1 and 2n, just you can write, but for finding the value of from there and a derivative, just we use here 2n minus 1 and 2n. Just have to writing like this. Okay. So this is the Maclaurin's theorem or Maclaurin's formula for the given function sin x. Okay. Similarly, you can find for cos x, etc. Okay. But just use formula and then find up to all order derivatives. Before 5, 6 derivatives are just you try to find and then write an nth derivative. Use here. Okay. And now question third. So question third is just here write Taylor's formula. Here Maclaurin's formula. Now just write Taylor's formula. Okay. For a given function, any type of function. Here just see the question. Write Taylor's formula for the function of y equals to fx equal to root x. Okay. With Lagrange's remainder with a equals to 1 and n equals to 3 is here. Just how can we write the formula? Just like we write formula for the sin x now, just now, Maclaurin theorem or formula. Here Taylor theorem or Taylor formula can also we can write with remainder form. With remainder form. So here just see the question. Here given what? Fx equals to root x. Fx equal to root x. It is y equals to root x. Okay. Lagrange's remainder a equal to 1. Just y equals to this given. Okay. And A equals to 1, n equals to 3. We have to write Taylor's formula or theorem for with Lagrange's remainder form. With n equals to 3. We know that Taylor's formula or theorem. Just you can write also anything. Theorem with Lagrange's Taylor theorem with Lagrange's remainder form is fx equals to what? Fx equals to, we can write here a equals to 1. So what? A equals to 1, not 0. A equals to 0, then about origin. A equals to 1 means about 1. So we can write f a plus x minus a, f dash a plus f square by 2 factorial, f double dash a plus r3, where r3 equals to what? X minus a 3 upon 3 factorial. Okay? F triple dash what? A plus theta x minus a. This. Just we write this formula. We will write this formula for the given function. Here a equals to 1. So we get fx equals to what? Root x implies f dash x equals to minus f dash equals to minus 1 upon root x, that is minus 1 upon x to the power half. Okay? F double dash x equals to plus half 1 upon x to the power 3 by 2. F triple dash x equals to minus 3 by 4 1 upon x to the power 5 by 2. So just like this. Okay, here minus 1 by 4, sorry, this is 1 by 2, here minus 1 upon 2, minus 1 by 2, this minus 1 by 2, okay. Now here 4, 1 by 4 is this, okay, and this is 8. If x equals to minus 1 by 4 this, and the minus 1 by 2, minus minus 1 by 4, 1 upon x to the power 3 by 2 minus this. So here f, now first just find derivative. F dash x means 1 by 2 root x, that is 1 by 2 into 1 by x to the power 1 by 2. So just now minus sign, 1 by 2 into 1 by 2, 1 upon x to the power 3 by 2, that is minus 1 by 4 x to the power 3 by 2. So this here, now minus minus plus, so 1 by 4 3 by 2, 1 upon x to the power 5 by 2, so that is 3 by 8 x to the power 5 by 2. So this is the value. Okay, here f is this, f dash is this, f double dash is this, f triple dash is this. Just you have to find all the derivative. So here just we see that f dash a equals to 1, so f dash 1, f1 is equals to what? f1 root 1 equals to 1. Now here just find value f dash 1, a1, f dash 1, f dash 1. So what? This 1 by 2, x equal to 1 by 2. Here f double dash 1, f double dash a, f double dash 1. So f double dash 1 is equal to minus 1 by 4, minus 1 by 4. Here f triple dash, a triple dash, here a equals to what? 1 theta x minus a. So here just we have to write what? 1 plus theta x minus 1. This we require. Okay, so this is equals to what? Just see here. X means 1 plus theta x minus 1. So f here we see that 3 by 8 x to the power. X means what? This. So this is power. This power 1 plus theta x minus 1 or minus 5 by 2. Just we can write like this. Okay. 1 plus theta x minus 1. So these are the values. Just find values. Find the value of derivative, find the value of function. Just here a equal to 1. So f1, 1, 1, 1 in all the places 1. So just using all these values, thus using all these values, in 1 we get all these values in 1 we get what? Fx, f pa means f1 1 plus x minus 1 f dash 1 half 1 by 2, okay, plus f double dash minus, so minus 1 by 4 x minus 1 square, x minus 1 square upon 2 factorial plus R3 can be written x minus 1 power 3 upon 3 factorial into this just 3 by 8 into 1 upon 3 factorial x minus 1 power 3 and this 1 plus theta x minus 1 power minus 5 by 2. So this is the required Taylor's formula for given function. Okay, which is required Taylor's formula for given function. Just write the value. Okay, 1 plus half x minus 1, 1 plus half x minus 1, 1 minus 1 by, just you can solve finally 1 by 4, 2, 2, 8. We can write 1 by 8 here, 1 by 8. Just here also 3, 1 by 16 in this place, just you can write 1 by 16. After solving 3 cancel into 16. So 1 plus half x minus 1 minus 1 plus half x minus 1 minus 1 by 8 x minus 1 square plus x minus 1 cube and this. Okay. So this is Taylor's formula. Just use this. This is the Taylor's formula up to the r equals to n equals to 3. That is r equals to 3. So this is formula 1, 1, 1, 1. Just use 1, 1 and find all the derivatives and remainder also just put in the formula. So this is solution. Okay. So similarly, we can write Maclaurin's formula, Maclaurin's theorem and Taylor's theorem also using remainder form up to the term whatever be the given n equals to 3, 4, 2 and so on. So if there is nothing is given, then you have to write up to the nth term. That is the Taylor's formula, Maclaurin formula. Okay. Now take another question. Now take another question just like this. Okay, here if fx equal to log 1 plus x is given and x greater than 0 using Maclaurin's theorem to show that for theta is lies between 0 to 1, log 1 plus x equals to this. So here given we have to show that fx equals to log 1 plus x, x greater than 0. We have to show that log 1 plus x is less than, or no, sorry, this is equals to what? Log 1 plus x plus x square by 2 x minus x square by 2 plus x cube by 3 1 plus theta x cube by 3 1 plus just like this 1 x minus x square by 2 plus x cube by 3 1 plus theta x cube we have to prove, and also we have to deduce that x minus x square by 2 plus x cube by just log 1 plus x is less than x minus x square by 2 plus x cube by 3 x cube by 3 only. X cube by 3. Here x greater than 0. For x greater than 0. Log 1 plus x is less than this for x is greater than 0. Okay. So just this is given. We have to show that log 1 plus x equal to this by using Maclaurin's theorem. We have to show that this using Maclaurin's theorem for theta lies between 0. Here theta lies between 0 to 1. Clear? Where x greater than 0 also. We know that the Maclaurin's theorem. Maclaurin's theorem with remainder form. With Lagrange's remainder form up to R3, form R3 as follows. Just write Maclaurin theorem. Okay, with the Lagrange remainder form. Maclaurin's theorem. What? Fx equals to f0. Maclaurin theorem. f0 plus x f dash 0 plus f x square by 2 f double dash 0 then R3 is there. Where R3 equals to what? X cube by 3 f third derivative of theta x. Okay, that implies fx equals to f0 plus x f dash 0 plus x square by 2 f double dash 0 plus x cube by 3 f double dash theta x. Okay, so this just like this equation 1. The remainder R3 up to R3 like this. Clear? Now here just put all the values first, just we can see. Let here fx equals to what? Fx equals to log 1 plus x. Log 1 plus x. So implies f dash x equals to what? 1 upon 1 plus x into 1. Implies f double dash x equals to, because we require how many derivatives are there? Third derivative up to third derivative. So second derivative is 1 upon 1 plus x square, and third derivative minus plus 1 upon 1 plus x cube plus 2 minus plus 2 1 upon 1 plus x cube. Okay, so from here just this implies f0 equals to log 1 plus 0 equals to log 1 equals to 0. And here f dash 0, just find all the derivatives. F dash 0 equals to what? X equals to 0, 1. 1 upon 1 plus 0 equals to 1. Here f double dash 0 equals to what? Minus what? Minus 1 upon 1 plus 0 square equals to minus 1. Third derivative. If third derivative theta x, just theta x, because third derivative with theta x, here theta x. So 2 upon 1 plus theta x cube. Okay, 1 plus theta x cube. So these are the values. Just this put here. Okay. After substituting these values in 1, we get C. So we can write here using all these values in 1, we get in this. Okay, in this. So just we can write. See here, fx means log 1 plus x. Fx equal to log 1 plus x. Here f0, 0, first value is 0. What? First value 0 plus second value x. First derivative 1, 1 into x, x. Now minus 1, and minus 1, this is equal to minus 1. So minus x square by 2 factorial plus this is equals to this plus x cube by 3 factorial into this value 2 by 1 plus theta x cube. Theta x cube. So this is the value. Now implies log 1 plus x equals to x minus x square by 2 plus x cube by 3 1 plus theta x cube. So proved. Okay, here theta lies between 0 to 1. And I want to theorem. Okay, so here 3 into 2, 2 to cancel 3. Now for proving this, for deducing this, also x greater than 0 and theta greater than 0 implies theta x greater than 0 implies 1 plus theta x greater than 1. Just add theta greater x greater than 0, theta greater than both multiplication greater than 0, just plus 1 on both sides. This implies what? Just revert is 1 plus theta x. Just we can also cube it first. Okay. Here 1 plus theta x cube is greater than 1. It is also right. 1 cube. Just cube it. 1 cube means what? 1 upon 1 plus theta x cube. Invert it, then this is will be less than 1 upon 1. 1 upon 1. Okay. Now, just by using it, we see that 1 upon 1 plus theta x cube is less than 1, implies just multiply x cube on both sides. X is greater than 0. So, x cube. We can write like this. Okay. Also, we can write like this. Clear? Now we can add on both sides. X minus x square by 2 plus x cube by 3 1 plus x theta x cube less than x minus x square by 2 plus x cube by 3 1 plus theta x cube. Just this quantity is less than here this x cube by 3. So x cube by 3. Just what we here do? Just this multiply on both sides x cube and divide by 3. Okay. Now add this 2 on both sides. So this quantity is less than this. This is given here. This is equation 2. This is proved first part. And this is equals to log 1 plus s. Using this is 3. Now just write. Using 2 and 3. Using 2 and 3, we get the required result as just use this 2. So this is equals to log 1 plus s. So log 1 plus is less than this. Okay. Question 3. As log 1 plus x is less than x minus x square by 2 plus x cube by 3, x greater than 0. Okay, x minus x square by 2 plus x cube by 3. Okay, so just you by using Maclaurin's theorem or Taylor's theorem with remainder form, you can get result as given in the questions. Okay.